All right, so we didn't even get to automorphisms and inner automorphisms in lecture A. So let's get there right now here in lecture B. First of all, recall that any group is isomorphic to itself. Certainly the identity mapping is an isomorphism. Right, it's definitely one-to-one and onto, definitely operation preserving. ID of x times y would be x times y, which is ID of x times ID of y. But there could be other isomorphisms from G to itself. Such isomorphisms go by the special name automorphism. Having trouble talking today. Such isomorphisms go by the special name automorphism. Self-morphism, like an autoimmune disease, is a disease where your body attacks itself. Self-isomorphic, but we don't say autoisomorphism, we just say automorphism. So the key thing here is every automorphism is an isomorphism. So that means it's definitely one-to-one onto an operation preserver. The new thing is it's from a group to itself. G to G. There are special kinds of automorphisms that are called inner automorphisms, and that sentence there, the is should not be there. There are special kinds of automorphisms called inner automorphisms. They have a special formula. Given an arbitrary A and G, we can define phi sub A, a mapping from G to itself, by this formula right there, phi sub A of x. It's not like the left representation. It's not A times x, it's A times x times A inverse. We should verify that this is one-to-one, that this is, now we can verify it's one-to-one onto an operation preserving. If, using the new notation, if phi sub A of x equals phi sub A of y, that will imply AX A inverse equals AY A inverse, which by left cancellation and right cancellation, cancel the A's on the left and the A inverses on the right, implies X equals Y. If you wanted to show steps and not just say by cancellation, you could write this kind of thing first, and then use the associative property to group together the A inverses and the A's to get the identity to ultimately see that X equals Y. But you can just say cancellation. That would verify the function's one-to-one. Is it onto? Well, that would be essentially a matter of, given Y and G, can you solve this equation for X? And does the logic go the other way? And the answer is yes. Multiply on the left by A inverse and on the right by A, and you would get X to be A inverse YA. Technically, you should verify that. Phi sub A of A inverse YA would be A times A inverse YA, A inverse, and then showing extra steps just for the fun of it. There we go. Hey, I never knew that I equals Y. Okay. Sorry, bad joke. Okay, it's definitely onto. Is it operation preserving? Come over here. Is this true? I'll put a question mark here. This is abstract, so operation preserving would be with respect to this multiplication on both sides. I think it's best if we think about that form first. This would equal AX A inverse times AY A inverse. Associative property. Brings you to A times xy times A inverse, which is phi sub A of xy. That does it. So it's one-to-one onto operation preserving from G to itself. It is an automorphism, but it's a special kind of automorphism. It's got a formula. In general, automorphisms might not have nice formulas. These inner automorphisms do. They have nice formulas. So every inner automorphism is an automorphism, but there could be some automorphisms that are not inner automorphisms. Let's see. Note, if A happens to be in the center of the group, so it commutes with everything in the group, then phi sub A actually is the same as phi sub E. So we could get repetitions. This is not the same as what we were doing in lecture A with the left regular representations. Each little g gave us a unique T sub G. And if I have a different element, call it H, where G and H are not the same, T sub G and T sub H are not going to be the same. G bar had the same cardinality, the same order as G did. This has to be the case. G and G bar were isomorphic. Here, with these inner automorphisms, you can get repeats. The set of all inner automorphisms can have an order or cardinality smaller than the original group. There could be repeats. I'm going to assign an exercise where that is made a bit more precise. Okay. Turns out the collection of all automorphisms and the collection of all inner automorphisms form groups under function composition. These groups are denoted by aut G and in G. And obviously, in G is a subgroup of aut G. Also note that because of the note on the last slide that if A was in the center of G, then phi sub A equal to phi sub E, in that case, that if G is abelian, so its center is the whole group, then the inner set of inner automorphisms is going to be trivial. Just the identity map. If G is abelian, phi sub A of x, which equals AX A inverse, because G is abelian, would equal also XA A inverse XE, which is X. The identity mapping, no matter what A is. If G is abelian. That's the same as phi sub E of x. Then in G just consists of the identity mapping. It's a trivial group. So somehow in G is related to the center of G, and maybe not just in cases where G is abelian. We're going to see that in chapters 9 and 10. In G and the center of G are related. If you can understand one, then you can understand the other. With a whole group of helping you understand G itself as well. Here's a theorem that says can be described as the group of all automorphisms of a finite cyclic group is isomorphic to the group of units mod n. Aut Zn is isomorphic to Un. The group of automorphisms of Zn is isomorphic to Un. That says, for one thing, for example, that aut Z8 is isomorphic to U8. That would tell you, since U8 has 4 elements in it, it would tell you, if nothing else, that aut Z8 has 4 elements too. there are 4 automorphisms from Z8 to itself. What are they? Come to that here in a minute. What's the idea of the proof here? I'm going to go through this quicker than Cayley's theorem, and it's still pretty difficult, but we need to go through it quicker. If we're going to show they're isomorphic, I better come up with an isomorphism. Going with the book's notation here, T, probably would have been better to call it phi, since phi has been reserved for isomorphisms. And this makes us think of the left regular representations from Cayley's theorem. But it's not the same. This is going to be our isomorphism. Map an arbitrary automorphism of Zn to itself. Call that arbitrary automorphism alpha. Alpha is a function from Zn to itself. T is going to map it to its value at 1, at the input 1. Zn as a set consists of 0, 1, 2, 3, etc. through n minus 1. Right? It's got 1 in there. What is the output of an arbitrary automorphism of Zn at 1? That's what we're going to define T alpha to be. Kind of strange. That's maybe not so obviously the only thing you could do. And in fact, it's not the only thing you could do. You could do more. You could do other things. You could define this isomorphism in other ways. Here's a key comment. An automorphism of Zn is completely determined by its value at the input 1. Alpha, an automorphism of Zn to itself, is completely determined as a function by whatever its value is at 1. Why? Because its value at some other input, k in Zn, since alpha is operation preserving, and since the group addition in Zn is addition, I could write this. Oops. Thinking of k as a positive integer here, and in fact less than n, here's where the fact that alpha is operation preserving comes into play. It's an automorphism, so the operation in the target is also addition. It's mapping Zn to itself. This is also k times. In other words, this is the same as k alpha of 1. So if you know what alpha of 1 is, you can figure out what alpha of k is. This is analogous to a linear algebra. If you can define a linear transformation just in the basis vectors, then you can define it for all vectors in the vector space. It's analogous to that, if you remember that from linear algebra. Basis vectors, right? Scary word, basis. Now, actually, maybe it doesn't feel so scary right now, right, compared to this stuff. If you thought basis was scary in linear algebra, okay, do group theory. Then it doesn't seem quite as scary. Okay, so it's completely determined by its value of 1. And this fact also means T is 1 to 1. Alpha of 1 is going to be an element of UN. That would technically need to be verified, that really this is in UN, that it's relatively prime to N. Why would that have to be the case? That's not completely obvious, I don't think. Well, here's a quick explanation. 1 is a generator of Zn. It's got order n. Alpha, being an automorphism and is also an isomorphism, has to map 1 to something else that has order n as well in Zn. It's got to be a generator of Zn. And the generators of Zn are relatively prime to n. Generators of Z8 are 1, 3, 5, and 7, the elements of U8 that I erased. Alpha alpha of 1's got to be one of those four things in this example with Z8. If n were 8. That's what I'm mentioning here. Turns out you can also show T as 1-to-1 and onto an operation preserve. Is this useful? It's not clear. But it's building up tools that might be useful. Okay? And they are useful in our mathematical taxonomy in classifying groups, it turns out. All right, let's go on to now Lagrange's theorem and cosets to end class today. I'm mostly going to focus on cosets today. But let's quickly remind you what Lagrange's theorem says. It's also known as the fundamental theorem of finite group theory. Actually, I added the word finite in there from last time. I really should have had finite in there last time. Lagrange's theorem applies to finite groups, not infinite groups, at least as we're stating here. If G is a finite group and H is a subgroup of G, then the order of H divides the order of G. We already knew that was true for cyclic groups in chapter 4. This is saying it's true for arbitrary groups. One thing that's not true, however, that was true for cyclic groups, is that the number of subgroups of the given order that divides M is not necessarily unique. It's not necessarily one subgroup of each order. In fact, you know, for example, in D4, there are many subgroups, distinct subgroups from, for example, order 2. Take any reflection, it's got order 2. Cyclic subgroup it generates has order 2. And they're all distinct because they all have different reflections in them. There's 4 of those. There's also R180. It's got order 2. There's 5 subgroups of order 2 in D4. Not a unique subgroup of order 5 or order 2. Okay, so that's not true in general that you would get a unique subgroup of each order. Moreover, the number of left cosets, as we'll define here in a second, and also right cosets, is the quotient, the order of G divided by the order of H. This quantity, by the way, has got a name. It's called the index of G and H. I'll talk more about that after spring break. A couple corollaries. One's easy to prove, one's harder. In a finite group, the order of each element divides the order of the group because an element of a given order is going to generate a cyclic subgroup of that order. So that subgroup's then got to divide the order of the group. Its order has to divide the order of the group, so the order of the element has to divide the order of the group too. Harder to prove is, for example, this corollary. If P is a prime greater than 2 and G is a group of order 2P, then G is isomorphic to only 2 possibilities. G is either cyclic or it's isomorphic to DP. There's only 2 possible isomorphism classes for groups of order 3, or excuse me, 6, 2 times 3. What else? 10, 2 times 5. 14, 2 times 7. 22, 2 times 11. 26, 2 times 13, etc. Only 2 isomorphic groups that could be isomorphic too. All right, now we're on to cosets. What are cosets? You've read about these things. You can think of them as tools to prove Lagrange's theorem, and they certainly do, but they end up being important in their own right. See chapter 9. Let G be a group and let H be a non-empty subset of G, not necessarily a subgroup initially, though we will be mostly concerned with situations where H is a subgroup. Notationally, we're going to use these things here. Aha and aha. No. AH, HA, and AH, A inverse. Actually, when I was your age, I never bothered saying aha and aha. And then aha doesn't quite work with this one anyway. but now that I'm older, I feel like saying it. I took Eric Cosset for algebraic structures, and he never said aha. So I guess I didn't either. He had too much reverence for it. These are sets. H is a subset of G. Consider the set of all products, little a times little h, as little h ranges over capital H. The set capital H. We can consider this set, the set of all products HA, as h ranges over capital H. And the collection of all products A inverse as h ranges over capital H. Okay, H doesn't have to be a subgroup to use this notation. And sometimes it's useful to use this notation even when H is not a subgroup. However, we are most concerned about when H is a subgroup. In such a situation, then these things have special names, at least the first two do. AH is called the left coset of H in G containing A. HA is called the right coset of H in G containing A. Let me make these boldface. The element A is called a coset representative of both HA and HA. And we'll use our usual notation for the number of elements. Absolute value signs, but you really shouldn't call them absolute value signs. Oops, that was bad. So if H is a subgroup, then these sets, again, have special names. Let's take it as an example, D3. And let's go ahead and take H to be a subgroup. Let's take it to be the subgroup generated by V. Don't get confused here. H is not a reflection. H is the cyclic subgroup generated by V. It's the set consisting of these two elements. What are the left and right cosets? One left coset would be VH. Maybe I should make H bigger. Maybe I should even do this. I don't think I'll bother after this point. That's going to be the set of all products, V on the left, with elements of H. Set of all products would be then these two things. Which is going to be the same set as the original set, H. This equals H. Well, I guess I am doing it. The left coset containing V does contain V. Same with the right coset. Okay. I could do something similar with an R0 instead of a V, and I get the same sets. This is the same as R0H. Whether I put the R0 on the left or the right. Seems like kind of a dumb concept so far, doesn't it? Like, what's the point? Well, let's consider another example. Let's try the left coset containing D. Multiply by D on the left. I better go back to my Taylor table here. D times R0 is D. What's D times V? D composed with V, R120. This is the left coset of H containing D, and it does contain D. It also happens to contain R120. What if I did the right coset of H and G containing D? Now multiply by D on the right. D3 is non-abelian. Will I get something different, a different set? I still get D in the set, but V times D is R240, not R120. That's making the concept start to seem a little bit more interesting. This one also does equal R120. H, it does contain R120. This one also does equal H R240 on the right. But notice DH in this case does not equal HD. These are two different sets here. They have the same size, the same cardinality, but they are different sets. But they both contain D. As a left coset, this one also contains R120. As a right coset, this one also contains R240. How could this possibly have any applications? Well, again, the first application is a tool to prove Lagrange's theorem. But anyway, I could keep going with this example. Let's instead spend our last few minutes looking at the properties of cosets. First of all, A is always an element of AH and HA for that matter. So our terminology saying that AH is the left coset of H in G containing A, and HA is the right coset of H in G containing A, that terminology is not bad terminology. A is in both sets. Why? Quick proof would be, since H is a subgroup of G, it's got the identity element in it, E. And A does equal A times E. A is of the form something, A times something in H. It also equals E times A. It's of the form something in H times A. H is assumed to be a subgroup of G here, so it's got the identity in it. I seem to have lost my clicker. Does everyone see where I put it down?
It's on the whiteboard thing.
Oh, thanks. The left coset of H and G containing A equals H itself if and only if A is an element of H. So it's not that it just contains A, but if A is in H, this left coset will equal H itself. Just like with this example, V was in H, so VH equal to H, and equal to HB as well. Down there. There's a kind of associativity here. And this is actually really important once we get to chapter 9. AB, H, the left coset of H and G containing AB, equals A, BH. Here's where that distinction between H being a group, a subgroup of G, and or perhaps just being a subset of G is important. BH doesn't have to be a subgroup of G. And in fact, if B is not in H, BH will not be a subgroup of G. So we do need that notation to apply even when this is not a subgroup. And A times this thing still makes sense as a set. This is the set of all elements of G that are A times something in here. But the thing here, if B is not an H, is not going to be a subgroup of G. Similar kind of thing holds for right cosets. AH equals BH. We're about out of time. If and only if A is an element of BH. And then there's some other properties. Yeah, we're about out of time. So this is, again, a weird concept. And now you've got 2 weeks until our next class, when we're going to go back to talking about this more. So, you know, you got to continue thinking about it. I would even encourage you to maybe watch videos about it over spring break, too, once in a while, just to keep it a little fresh in your mind. Have a good spring break.